So 12576 comma 4052. HCF of 12576 comma 4052. Yeah. So yeah, let's do it again. So for this, what like so we are using this lemma, right? What is the lemma? Euclid's division lemma. So Euclid's division lemma says that we can express 12576 as some quotient into 4052 plus remainder, right? So what is the quotient? Can you say from yesterday's, what is the quotient and what is the remainder? Yesterday we calculated, right? Tarun, what is the quotient? 3 is the quotient, and what is the remainder? So 420. So now what we are considering, we are taking so 4, which is bigger, we'll take a left side, right? Which is a bigger, we take a left side, and then so again we take a 3. What is the quotient? We are taking, sorry, 4052, right? Sorry.
So we do some 2 into 1.
Right.
Plus 1.
So again 4052 420 9. What is the remainder? 272. So why we are doing like this? So we are saying that HCF of 12576 comma 4052 is equal to HCF of 4052 comma 420. That's what we are telling, right? That's why we are able to do this. Otherwise we can't do this, right? Can you prove it? So what we are saying, HCF of,
It's because it's a factor of 4052 and 420 is a factor of 12576 and 405.
say it again.
I think that 12576 and 4052 has a factor which is 4052 and 420.
But it can be a factor, but we are saying the HCF of both of them are same, right?
Yes.
It's not just a factor, but we are saying HCF of both of them is same.
Since they're a factor,
So it can be a factor, but how can you say that it's a HCF? Right? Let's say there can be a common factor of, so there can be a common factor between 12576, 4052 and 4052 and what is this number? 420, right? So there can be a common factor. But how can you say that that's a HCF? Or that common factor is a HCF? So once that is valid, then we can say that that's a way to calculate HCF. Otherwise we can't calculate in that way, right? So did you understand what I'm saying? So we want to calculate HCF of, let's say, A comma B, right? Let's say I think Kaushik is logged off, is it? So let's consider C. Can you try, Tarun, to prove it? Can you try proving it? Princey, did you understand the point? Can you try proving it? I'll tell you, yeah?
Recording in progress.
Let's say I have two numbers, let's say C and D, yeah. So we are expressing using Euclid's lemma C equal to dq plus R. So what we are saying here, HCF of C comma D is equal to HCF of D comma R. That's why we are able to go to the steps, next step, right? So if this is, again it's like that. So if this is not valid, we can't do it. So first thing is we need to prove HCF of C comma D is equal to HCF of D comma R. So any idea how can? So that would be, we don't want to go to prime factorization. We want to prove with what the things that we already know, just with the lemma Euclid's lemma that we have, right? Or simple from simple.
Maybe the quotient and the remainder of C comma D will be equal to the quotient and remainder of D comma R.
That won't happen, right?
Maybe the quotient of C comma D can be divisible by the quotient of D comma R. And the remainder.
Yeah, let's say you consider, like let's say K is a HCF of C comma D, right? Then we can, let's say C equal to dq plus R. So if K is a, so K is a HCF, so we can divide by K, right? dq plus R by K. It should be divisible. So it's divisible by K. It is divisible by Q also, right? So it should be integer. So then it should be divisible by R also, right? So it should be integer again. So K is a factor of R, right? So K is a factor of R, K is a factor of D, K is a factor of C, right? C. So but so let's say now consider now also we are saying, let's say HCF of D comma R is equal to some L, okay. So consider D is equal to L of L some A1, consider R L A2, is it right? Because L is a factor, right? L is a HCF, we can write it as a, so now can you express C L of A1Q into equation dq plus R, L of A2. If you take out L, A1Q plus A2. So again L is the common factor of C, right? So from this so L is a common factor of D also, right? L is a common factor of D and R. L is a common factor of C and D. So from this we know that L is a common factor of C. So from here we know that L is a common factor of D, right? So it says that, so HCF means so it's so what is K must be always greater than or equal to L, right? L is a common factor, but K is a HCF, so it's the highest common factor. So always K must be greater than or equal to L, right? Now we need to show that L must be greater than or equal to K.
So if K is equal to L, then it won't be the highest common factor. Or if it's equal to L, then L will be the highest common factor.
Yeah. So this says that K must be greater than or equal to L, So we also need to show that L must be greater than or equal to K. Then we can say that K is equal to L. So can you show that from this L is equal to greater than or equal to K? So this is the one inequality we have. Also we want to show that L must be greater than or equal to K. Can you try showing it? So now also we need to show that. So also we from the, so K is a factor of R, right? K is a factor of R. So it says that K must be less than or equal to L, right? So from these both we can say that K is equal to L. Is it clear? So what we are showing is, let's say we are taking HCF of C comma D some value, okay, and also we are taking HCF of D comma R some value, and finally we are initially we are taking they are different, and finally we are showing that they are same, okay. So that's why we are able to do this. We are able to, right? So you are not so clear, yeah? Okay. You are clear?
Just we need to just prove that K is greater or equal to R and L is greater or equal to K.
Yeah, right. L and T, right?
So should we repeat the process, the same process with D and R?
Yeah. So yeah, if you do the same process, then it says that K must be less than or equal to L, right? Then you can say that K is equal to L. Yeah, you can prove it many ways, but you can prove it many ways. This is the one of the ways that you can prove it. Okay, I'll explain you maybe later of the class. Yeah, I'll explain you. Are you clear with this? No, right? Okay. So let's say so we have that Euclid's division lemma, right? So it says that C equal to dq plus R. So that's a, so here R varies from 0 to 0 less than or equal to R less than. What is the bound for R? What is the bound for R? What is the bound for R? Bound. R varies from 0 to
R is
0 less than or equal to
Q, no B.
D, right? It varies from 0 to D.
So
D. Let's say
Here it is D,
it's
but it's not.
right. So whatever it is here, yeah. So it varies from 0 to D, right? So now, so how we are calculating HCF? So first we are let's say C is equal to dq plus R. We want to find out HCF of D comma C comma D, right? We want to find out HCF of C comma D. Now in the next step, what we are doing, we are taking here left side D and here R, and we are finding the quotient, finding out the remainder. So this is the process we are following, right? We are taking the D again to left side. Now we are taking R as a divider, right? And we want to find out the quotient and remainder. So when can we do this? When we can say that HCF of C comma D is equal to HCF of D comma R. If both are not equal, we can't do this, no? We want to find out of HCF of C comma D. But to find out that next step, what we are doing, we are saying we are doing HCF of D comma R. So if both are not equal, we can't do that. So in the first step, we want to find out HCF of C comma D. So second step, what we are finding out? We are finding out of HCF of D comma R. So both are different, no? So when can we do this? If both are equal, then we can say that that is a HCF of C comma D. So we want to prove that HCF of C comma D is equal to HCF of D comma R. So that's what we are doing. So if both are not equal, we can't proceed, no? So now you are clear with this? So to prove that only we just did the formulation, right? So let's say you take a HCF of C comma D is some K1. Then HCF of D comma R take some K2. Now we want to prove that K1 is equal to K2. So that is our goal of, right? K1 is equal to K2. So let's say if HCF of C comma D is equal to K1, then it should be divisible by both. It should be divisible by C, right? So what is the C? C is equal to DQ plus R, right? So if you divide by C by K, so it should be integer because it is divisible by K. C is divisible by K, so it should be integer, right? C by K is what? Integer. So also we are saying that it should be divisible by DQ plus R by C. So we are just dividing this equation, first equation 1, let's say equation 1 by K1. Okay? We are dividing the equation 1 by K1. So if you do that, that is C by K1 plus DQ by K1 plus R by K1. Right? So C by K1 is integer because K1 is a factor of C. Right? So also this must be integer because K1 is a factor of Q. So this is an integer, so this must be integer. So then K1 must be factor of R also, right? So we are saying that we already know that K1 is a factor of C and D. We want to show that K1 is also factor of R, right? So now let's say we are taking K2. K2 is a HCF of D comma R. So then we can express D as K2 into A, some factor, right? R as K2 into some B, right? So now you substitute this D and R in the equation 1. So then what it will be? C is equal to, Princey, can you say what is C now? If you substitute D and R in equation 1.
K2 AQ plus
Right? We are substituting D and R in equation 1. So what is the C now? K2 AQ plus K2B. So now you can take K2 common. K2 AQ plus B. So it says that K2 is a factor of C. Right? K2 is a factor of C. Also we are already saying that K2 is a factor of D. So that's what HCF of, we are saying HCF of D comma R is equal to K2. Right? It's already factor of D. Now we also know that it's a factor of C also. So, but it must be, so what is the HCF here? K1. So K1 must be always greater than or equal to K2. Because K1 is a HCF. K2 is just a factor. It can be HCF, it might be some factor. So K1 always must be greater than or equal to K2. Did you understand this point? So K2 is a factor, but K1 is also factor, but it is a HCF, means highest common factor. So that's why K1 always must be greater than or equal to K2. Right? Now clear? So now we want to show that K2 must be greater than or equal to K1. Then only we can say that K1 is equal to K2. So for that what we need to do? now also we need to show that K2, K1, yeah, K1 is a factor of R. We have shown that K1 is a factor of R. So K1 is a factor of R.
So we should prove R is less than or equal to 0. Less than
K2 is a factor of C and D. So now we need to show that K1 is a factor of D and R. Already we have shown that K1 is a factor of D and R. Already we have shown it.
K is a factor of D. So in the D, R, we can.
So already let's say K1 is a factor of D and R, right? So from here, but K1 is a factor of D and R. So, but K2 is the highest common factor. So K2 must be greater than or equal to K1, right? K1 is a factor of D and R, that we know. But what is the highest common factor of D and R? K2. So that says that K2 must be greater than or equal to K1. So from these two identities we can say that K1 is equal to K2. Is it clear? So we are taking HCF of C comma D as a K1, HCF of D comma R is K2. Okay? And we are saying that K2 is a HCF of C comma D equal to K1, HCF of D comma R equal to K2. And now we are proving that K2 is a factor of C and D, K1 is a factor of D and R. Now we are proving that K2 is a factor of C and D, K1 is a factor of D and R. But what is the highest common factor of D and R? K2. Highest factor of C and D is K1. But K1 is also factor of D and R. So that says that K1 must be always greater than or equal to K2. So also we are saying that K2 is a factor of C and D. But what is the highest factor? K1. So always K1 must be greater than or equal to K2. So from this both of them we can say that K1 is equal to K2. Okay, now clear? So that's why we are able to do it, otherwise we can't do it, right? So this is Euclid's division algorithm. So what is the Euclid's division algorithm? So let's say we want to find out HCF of A comma B, right? So then if the remainder is 0, what is the HCF of A comma B? Let's say A is greater than B.
Then
B is the remainder. So if that is not the case, what is the next step? If remainder is not the 0?
So we know that B would be greater than R.
Yeah, B always must be greater than or equal to R.
So we need to equate B will be equal to a value.
Now we are finding out the HCF of B comma R.
Repeat the process until
Right.
we get R.
Until we get R is equal to 0, we are doing this process. This is called Euclid's division algorithm. Okay. So this proof is, you are clear with the proof, right? Clear with the proof. So can you try this one? Show that every positive even integer is of the form 2q and that every positive odd integer of the form 2q plus 1. Let q is some integer. Every positive even integer is of the form 2q and that odd integer of the form 2q plus 1. So using that Euclid's lemma, try to prove it. Kaushik? Kaushik?
Yes, sir.
Yeah, so could you understand the proof that we did before?
Already, yes, sir.
Okay. So like,
Your voice was breaking.
oh, my voice is breaking.
The middle, there's an network issue. I had asked the doubt next class.
Okay. So you will join next class offline, right?
Yeah, after.
Okay.
Today, I'm not free.
Sure. So what a Euclid's division lemma says? If there are a and b are two integers, positive integers, we can express a is equal to pq plus r, right? Let's say consider b is equal to 2, right?
So R would be
A is equal to 2q plus r. So what is the r values? Where is from?
1 and 2.
0, 1, not 1 and 2, right?
It's not equal to B.
It's not equal to b. So r values are 0, 1. So if you substitute 0, a is equal to 2r, 2q, right? Sorry, 2q. If you substitute 1, it's 2q plus 1. So 2q is a even, 2q plus 1 is r, right? Rohit, is it clear? Anirudh, you are able to follow? Can you try proving this one? Show that any positive odd integer is of the form 4q plus 1 or 4q plus 3. So what the value b you need to consider here?
So for 4q plus 1, R would be 0, 1, 2 or 3. For 4q plus 3, R would be 0, 1, 2 or 3. So if you just say 4q plus 1 would be odd, 4q plus 2 would be even, 4q plus 3 would be odd. Till that we need to do that till 3 and we should show that 4q plus 1 and 4q plus 3 are odd.
So yeah, if you consider b is equal to 4, so it will be 4q plus 1, 4q plus 2, 4q plus 3. So 4q plus 2 are even, 4q plus 1, 4q plus 3 are odd.
So we can also use a trial and error method where we can substitute the value of q into something else and we can do it.
Yeah, but yeah, we need to prove it, no? So using a Euclid's lemma, we need to prove it. Yeah, if you like substitute any quotient, any integer, let's say, so it can be, so it will be like odd, right? Always 4q will be even, right? 4q will be even, right? 4q is always divisible by 2, no? 4q is always divisible by 2, right? That's why always 4q is even. So did you understand this one? No, right? So let's say consider b is equal to 4. So then how you can express, let's say A equal to BQ plus R, consider B is equal to 4. So now what is A? 4Q plus R. A is equal to 4Q plus R. So what are the values, range of values of R can take? Rohit, can you say? What are the values R can take? No. Like here, R has a particular range of values. R can take. What are the values R can take? So the range of R is 0 less than or equal to R less than B, right?
So R would be 0,
0, 1, 2, 3. So what is the Euclid's lemma? Let's say A is equal to BQ plus R. What are the range of values of R? 0 to? So let's say here we are taking B is equal to 4. So that's why 0 to 3. Let's say B is equal to 10. 0 to 9, right? So here R varies from 0 to 3. So now what is the, so A can be 4Q plus 1, 4Q plus 2, 4Q plus 3. But what we need an odd integer. So this here A can be even integer. So what are the possible integers? Even integer or odd integer. So here A can be even integer or A can be odd integer. So in these 4 possibilities, which are the odd integers? 4Q plus 1 and 4Q plus 3. 4Q and 4Q plus 2 are even. So that's a proof, right? So we want to, using a Euclid's lemma, we want to show that 4Q plus 1 or 4Q plus 3. So our odd integers are in the form of 4Q plus 1 and 4Q plus 3. So if you take a B is equal to 8, I will ask Rohit. B is equal to 8 here. Let's consider B is equal to 8. So what are the form of even integers? 8Q. Good.
8Q plus 4, 8Q plus 6.
Right? You need to consider till 6, not 8. 8Q, 8Q plus 2, 8Q plus 4, 8Q plus 6, right? So if you consider 6, Anirudh, can you say, if you consider B equal to 6, can you say what are the forms of even integers? B is equal to 6. If B is equal to 6, how can you express A? A is equal to? If B equal to 6, how can you express A? A is equal to BQ plus R, right? So we are considering B is 6. So A is equal to 6Q plus R. So what are the range of R values? 0 to 5. Good. So now what are the forms of odd integers? 6Q. You need to say complete, no? 6Q plus, yeah, 6Q plus R. So what are the R values that it can take? So R can take 0 to 5, right? But to become odd integer, what are the R values? 6Q plus 5. So now you are clear with this problem, right? Particular thing, right? So yesterday we have solved this question, no? Right? So what we need to find out here, HCF of 420, 130. Can you do it again? Do it again and show it to me. All of you. HCF of 420 comma 130. Kaushik?
Then, sir.
Kaushik, can you say what is the 420, what's the quotient and what is the remainder?
The quotient is 3 and the remainder is 30.
So yeah, next what we need to consider? Left side?
30,
30,
3 plus 3.
one.
HCF is 3.
So what we need to consider next? Left side. One 30, right?
30
So
30
30,
plus
30 into 4 plus 10. So what we need to consider next? 30, 10, 3. Right? So now what is the HCF? 10. Now clear, yeah? So here we are saying that HCF of, so can you say what is here what are equal? HCF of 420 comma 130 is equal to HCF of
30 is 10.
hmm?
HCF of 420 and 30 is
130 comma 30 is equal to HCF of
30,
30 comma 10 is equal to 10. Clear, yeah? Rohit, now clear, yeah? Anirudh, clear? I think yesterday you did for 867 and 255, right? 867, 255 you did, or? Okay, can you try for a? Okay, can you do it for 867 and 255?
So next question.
Sorry?
Next question, sir.
Yeah, next question. Can you do it for the third one?
The third.
Yeah, that third part, 867 and 255. What is the HCF? So what is the quotient?
so 3.
3 is the quotient. What is the remainder?
So it's 867 minus 192.
192. Into 1.
33, sir.
No. 55 plus 8, right? 63.
So it's 30.
Huh?
It's 225, sir. 255.
Oh, it's a 220, 255, right? Then it's a wrong. What's the remainder? Remainder is correct?
No, sir. It's
Okay, then.
It is for 220.
Okay, tell me what's the remainder?
It's 3.
3 is correct. Princey, what's the remainder?
1 or 2, sir.
1 or 2?
Yes, sir. It's 51, sir.
1 or 2? 2?
51 into 2
Yeah,
plus 0. HCF is 51.
51. Very good. Next?
1 or 2 equals 51 into 2 plus 0.
So what is the HCF now?
51.
51. So now tell me what are HCF of 867 comma 255 is equal to
255.
HCF of 255 comma 102 is equal to HCF of
102.
1051 is equal to 51. Clear? Anirudh, you could do it or you need some time? You do it, yeah? Good, very good. Can you try this one? I think we have already did this, yeah? We already did this. So what are the possible forms? All possible forms? 6q
Plus 1, 62 plus 2, 62 plus 3, 62 plus 4, 62 plus 5.
plus 2 plus 3 plus 4 plus 5. So what are odd here?
62 plus 1
Plus 1
3
plus 3 plus 5. So can you express every number with these forms? Every positive natural number, can you express with this? Right? If you take q equal to, let's say q equal to 0. So what are the values?
0.
0 to 5.
Yes, 0, 1,
0 to 5. If you take q is equal to 1,
6.
6 to 11.
Sir.
Q equal to 2, 12 to 17. So like that you can express every number. Right? So that's what the Euclid's lemma says, right? Can you try this one? So first read the question. Anirudh, can you read the question? They can march. So what do you need to find out here? Huh? LCM or HCF?
Maximum number of columns is LCM is always critical. So
Maximum number of columns in which they can march.
I think it's LCM.
It's a HCF, right?
I think it's LCM.
Maximum number of columns in which they can march.
Okay, sir.
Kaushik,
Yes, sir.
what do you think? It's a HCF or LCM?
HCF.
HCF, right?
HCF.
Yeah. So can you find out HCF of 61632?
Yes, sir. Right.
Anirudh, can you please tell me the quotients this time? 616 is equal to 32. What is the quotient?
Maybe. The quotient is
19,
19.
yeah?
19. Remainder is 8.
Quotient is 19 or 18?
19.
19. Remainder is
8.
8. So now what is the quotient?
Quotient is 4.
40.
And the remainder is
So now HCF is 8. So now HCF of 616 comma 32 is equal to HCF of 32 comma 8 is equal to 8. Yeah, can you try solving this problem? So follow the hint here. What the hint they provided, follow the hint. Use Euclid's lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1.
Use identities.
Sorry?
We need to use identities. If we need to square, we need to use identities. For example, if it's 3q square, we get 9q square. So if we express it in the form of 3m or 3m plus 1, it will be 3 into 3q square, but 3q square is m, which is some integer. So it will come under 3m.
So there will be m is 3q square.
3q square. 3q will be some integer.
3q square.
If we follow it with 3q plus 1, if we square it, we need to use the identity x square plus b square.
Can you do it? 3q plus 1. Did you understand what you need to do? Didn't understand? So express, right? Like using a Euclid's lemma, express x equal to it's maybe some 5 minutes. Okay. So here express x is equal to 3q plus r. Okay. So here r can be 0, 1, 2. So x can be 3q, or 3q plus 1, or 3q plus 2.
So you will get 9q square plus 1 plus 6q. So it will be 9q square plus 6q. If we take common factors, so we will get 3q brackets 3q plus 2, where 3q plus 2 is n, which is some integer.
Right. So now consider case when x is equal to 3q. This is a case 1. Okay. Case 1, x equal to 3q. Now what we need to do? We need to square it. Square of any positive integer we need, no? What is the square of 3q? It's a 9q square. So we need to show that it is equal to either in the form of 3m or in the form of 3m plus 1. So how can you express 9q square in terms of 3m? 9q square can be written as 3 into 3q square. So we can take 3q square as some m. It's a 3m. Right? Now can you do it for the 3q plus 1 case? Now take case 2, 3q plus 1, square it and express either in the form of 3m or either in the form of 3m plus 1. Kaushik? So what is the square of 3q plus 1? Rohit? 9q square? 3q plus 1 whole square. 9q square plus?
Plus 6q.
A plus, what is it? A plus b whole square formula. A plus b whole square formula. What is the A plus b whole square formula? A plus b whole square. So what is it now 3q plus 1 whole square? 3q plus 1 whole square. Tarun?
Yes, sir. 9q square
9q square
plus 6q plus 1.
plus 6q plus 1. Now we need to express either in terms of 3m or 3m plus 1.
So we need take 3 as common.
3 as common, then
3 as common.
uh,
Then you get
3q square
plus
2q plus 1. So this 3q square plus 2q can be m.
yeah.
So it is in the form of 3m plus 1. Not clear? So we are considering x is equal to 3q plus r, right? So what are the values of r it can take? 0, 0, 0, 1 and 2. So we have three cases. When r is 0, when r is 1, when r is 2. So now we are taking case 1 where r is 0. So here x is equal to 3q. Now what we need to do? We need to show for the square of any positive integer. So we have taken the positive integer, we need to show it for the square of it. So what is the square of 3q? 9q square. So 9q square we can write it as 3q square. Just we need to express in the form of 3m or 3m plus 1, no? So that's why we are splitting in terms. And then this will be, we can consider m. So it will be in the form of 3m. So now what is the case 2? Case 2 is 3q plus 1. So we have 3 cases, 3q plus 1, 3q plus 2. So now case 2 is 3q plus 1. So again what we need to do? We need to square it. So if we square it, what is the 9q square? Plus 6q plus 1. So here we can take out 3 common. So then 3q square plus 2q plus 1. This can be expressed as m. So it is the form of 3m plus 1. So now what is the case 3? What we need to do now? We need to do square it and express in terms of 3m or 3m plus 1. Can you do it?
So if you square 3q plus 2, you get in the form of 3m plus 2.
3m plus 2?
But it's not given there.
Can you try it? Did you do it? Do it. What is the 3q plus 2 whole square? Rohit? 3q plus 2 whole square? Nine q square plus 12q plus 4.
So you keep 4 as
So you can keep it as 3 plus 1. 3 plus 1.
So with 3 brackets 3q square plus 4q brackets close plus 4, where 3q square plus 4q is
I think somewhere it's wrong. You need to make it as 3m plus 1. What is the form you got? 3m?
plus 4.
But we need to show it in 3m plus 1. Can you show it in terms of 3m plus 1?
So it will be 9q square plus 3 plus 1. 9q square plus 3 plus 1
Right,
plus 20.
plus 1. So you need to split 4 as 3 plus 1 and then plus 1 will come there, right?